Yo, yo, yo. What's up, everybody? Welcome back. Today we are writing a PNG decoder because I think it would be fun. Yeah, I want to at some point work on like an image editor, and I feel like probably the very start of that project would be opening an image, right? So we could use the typical like STB image and pull it in or do whatever. But I think it would be fun to try to reduce dependencies, and I think there's like a good rationale, kind of in general, to say understanding like what data you're working with is, I think, generally kind of important. It helps you like diagnose issues that come up. Not that I really expect to see much issues in opening a PNG file, but I do think that it'd be nice for me to like have a handle on what they actually are, because I don't really know, right? So I think we're gonna just try to write a PNG decoder. We're gonna try to like get a PNG, make one, I don't know, stick it somewhere, try to open it, look at what's in it, see what happens. Yeah, and I guess that's kind of the extent. I was looking up a little bit. I looked up PNG, and then we got Pacific Northern Gas. Not helpful. But if we look up PNG image, that's also not helpful. What about PNG spec? Here we go. Finally, we get to the Wikipedia page. And this has like a kind of nice overview of what's in this thing. There's some sort of header. There's some sort of chunks. There are some form of like transparency, compression, as well as like deflate compressed data. But, screw looking at the Wikipedia page. In here, we can see RFC 2083, and you just type that in. Boom, we have the official spec. Let's fucking go. So I think we will start here. We know that there's like deflate compression associated with this thing, which we've looked at before in a previous set of streams, called zlib and zig. So we have implemented a zlib decoder before, but in happy hour for the past couple days, we have been experimenting with just like getting back into that mindset by implementing it again. So it's kind of like 3 hours ish of work to get like something that can decode a little bit of like a hello world. So we might use this. We'll kind of see how that goes. But we'll kind of like leave that decision for when we get to wherever we're getting to. So let's just start by making some image to play with, and then we will try to open it and figure out what the hell is going on. So what if we just made a really, really small smiley face? Right? Perfect. How do I paint bucket? Boom. Okay. And then let's just kind of save this as a PNG image. Hell yeah. I wonder if these are important. I'm not really going to think about it. I'll just pick the defaults, and let's go into lib image and just save this as smile.png. Presumably in the future, we're probably going to want to like handcraft these PNGs a little bit so that we can kind of test specific behaviors of like PNG encodings. But right now we don't really know what the fuck is going on. So I don't know. This seems fine. Perfect. There's our little smiley face. Cool. Let's try to open this thing. So I guess we should start a project. So let's take a zig environment from somewhere else and get into it. What's in this thing? We have zig, the language server, Valgrind, GDB, Python, libc. Sure, fuck it. That's good enough for now. Good enough for now. I guess we have successfully made a PNG. This probably didn't deserve its own chapter. So let's just pretend that we started something else at that point in time. Okay. Let's do our typical zig project setup. So make dir source, we say edit source main zig. We write out like, pub function main returns an error or nothing. And we just start by saying return error. Hello. To say that we can see some sort of behavior, and we set up our build zig to say pub function build. He takes in a builder, which is a pointer to std build. He returns a maybe error void, which means we need to send for library. So we import std, and we do our world's simplest setup where we say const executable is equal to b add executable. This executable comes from, we'll call this PNG test. And he's going to come from source main, I guess is what we called it. And we need an optimization level. So we say, give me some optimization level, please, and a target to compile for. Boom. Which means we have optimize equal opt and target equal target, and then we have to put this thing somewhere. So it'll be install artifact exe. Boom. Zig build. And zig out bin PNG test. Boom. Error hello. Sick. I guess we should get in it as well, and then probably set up a git ignore, which ignores zig cache. I think it's zig cache and zig out. Cool. And then zig build. I guess we try to open something. Okay. So we need the standard library. And let's just say that we have some file that is a, what do we call this thing? Open file. His name is Smile PNG. Okay. And I guess we're gonna have to do something with this, but I don't really know what yet. So maybe we don't do anything here at all, and we just kind of like hex dump this thing and take a look at it. So we can see PNG here is like a human readable string at the beginning, so we can probably assume that this is some sort of like magic identifier so that like programs can tell what type of file this is. We see like an I header fizz. These look like maybe like strings that have meaning, right? Some like real meaning. I end, I header sounds a lot like some form of like block chunk names. I think that I saw when I was skimming this earlier that each chunk, yeah, we have like an I header chunk. There are like critical chunks here. And I remember seeing that like if depending on the case of some of the letters in this chunk name, you should interpret this data differently. So let's look at like the, can we look at the overall file structure? That's probably a good place to start. A PNG file consists of a PNG structure followed by a series of chunks. This chapter defines the signature and the basic properties of chunks. Individual chunks are discussed in the next chapter. Jeez, I can't read. Okay, so here is the magic, 8 bytes. Okay. So the signature indicates the remainder of the file contains a single PNG image consisting of a series of chunks beginning with an I header chunk ending with IN. Cool. Chunk layout. Each chunk consists of 4 parts: a length, a chunk type and chunk data, and a CRC. Okay. There are naming conventions, which I think we can kind of ignore for a bit. And if that is the overall structure, and the overall structure has chunks that have length and type and data, then we should be able to just kind of walk this top level thing like almost immediately with very little information, right? So can we do something that's like, let's get an allocator in here, which we usually get from the general purpose allocator, which means we need a var general purpose allocator is equal to std heap general purpose allocator with I don't give a fuck arguments. And later we deinit this thing to make sure that we have freed all the memory we care about. We presumably have to close this file. And I guess we want to read the stuff in here. So we're going to say like const data is equal to f read to end alloc, and we need to specify a max size. So 1 megabyte seems fine. I don't really care. So we're going to have some data now, and we can just try to walk this data. So we know that we're supposed to see, where was it? This at the beginning. Right, so we can kind of just copy this. So like some sort of like unknown sized U8 buffer. And why is he expecting a comma? Oh, because here we're supposed to do this. Okay. So if we look at like data, can we do like data from 0 to ping header len? Can we do like a std? We can do like function is PNG, takes in data and returns bool, right? Simple. We take in this stuff, boom. I guess we say if data is less than PNG data len is less than PNG header len, we return false. Otherwise, return stood mem equal of PNG header and data from 0 to PNG header len. Okay. Okay. Right. Which means down here we can just call like stood debug print is PNG is flagged by is PNG of data. Boom. Okay. And this comes from Zig out bin, whatever we called it. He's mad because we don't use the allocator because we were supposed to pass it in here probably. Just forgot. And then mem equal requires us to specify this is a U8. I believe that the reason for this is because it allows for coercion from like arrays into slices in a way where the function, the generic function, doesn't have to it won't like create like a new function here for passed in as like this thing passed in as an array. So it doesn't have to make like equals for U8 10 byte slice, U8 12 byte slice. Like it kind of just figures out, this allows like better coercion, I think. Are you using Dern for next shell? Nope, don't even know what that is. We have to free the data later, and then we have a nice little happy is PNG true? And then I guess we don't need to return an error anymore because we're happy. So we have successfully identified this thing as a PNG, so we're chilling. Now we can just start like walking the chunks, which makes me kind of feel like we're gonna have some sort of like PNG decoder, I guess. And I guess for now he's going to work on data directly. Although maybe it would make more sense to like do this directly on the file input. But data's fine. And then we can just take like we could either like rewrite the length field of this data as we walk it, or we could keep like an index. I don't know, sure. And if we're trying to walk the chunks, presumably this is going to return some sort of chunk, right? And we know that each chunk has a length. He has a type, which is a 4-byte chunk type code. Data, and CRC, which I think is a U32 typically. Not sure. And let's kind of assume that we're going to do some work here. I don't really know what. I guess we are going to initialize this thing. And I think that we're going to take in probably like the buffer. Start the index at 0. And I think what we're going to do is here just say if that this is not a PNG. If not is PNG buff, return error not PNG, right? Otherwise, we can just say that self, maybe our index starts at PNG header len. Yeah. And then we can return data is equal to buff. Maybe we should just call this data here. Just for naming consistency. Hello. What's up? I felt like I said that one at like 4x speed. What's up? Okay. So he needs to walk these things. So I'm assuming that we can just say length is, maybe we want to do like something like try advance. Okay, and he's gonna take in by like a length. He's gonna return like a U8 slice or something. I don't know. I haven't really thought this through yet. But then we can do like self dot index plus equals len, and then we can say like if self index plus len is grade is too large, then return error end of file, I guess, is fine. Otherwise, we can do like return self data self IDX to self IDX plus len or something. I don't know. Seems reasonable to me. Seems reasonable. So then we call like self try advance by 4. We have the chunk type, chunk data. All of these are try here. And this is going to be try advance by length, right? And then CRC by 4. If ever Raven, thank you for the prime. Much appreciated. Much appreciated. Then we should be able to just return this, right? So it's almost like we can kind of do these ones inline. Oopsies. Like this. And then length is equal to length. Something like that. He's mad about something. I guess it's these semicolons. That makes sense. Been watching on YouTube, figured out how to catch live. Let's go! Happy to have you. Happy to have you. Okay, so now we should be able to like decode, like initialize this thing. So we should do like, I don't know, PNG decoder initialize with data, right? And do while decoder next chunk. We should be able to like print out the chunk type. Chunk type is going to be a string. I think it's pretty reasonable to view it that way. And let's just kind of see what we got. He's mad because try advance here. This thing needs to be failable, which means that this thing needs to type try. And then length here, we say expected use size found const u8. That's true. I don't know what the fuck we're fucking smoking here. Oh no, wait. Oh, here we have to do int from stood mem bytes to value as a u32. Now, is this big endian or little endian? The length counts 4-byte unsigned integer, giving the number of bytes in the chunk's data field. Length counts only the data field, not itself. The chunk type code or the CRC. Right, 0 is a valid length. And do they talk about like endian? No? Are you kidding me? How am I supposed to know data representation? Integers in byte order. Here we go. Here we go. Integers in byte order that require more than 1 byte must be in network byte order. The most significant byte comes first. Okay, sure. So we need to do like length big endian, or we'll call this length bytes. Then we say const length is equal to stood mem like endian. I know that there's like a read endian thing in Zig. I just can't remember what it is. We're on 0.13, and can we just look for like endian? Files, really? Just wondering what's happening with the Google Maps project. It was so cool. Yeah, I just kind of stopped being excited by it, so I stopped working on it. It's kind of just the way it goes sometimes. Native to little, big to native. Here we go. That's what we're looking for. Coffee enjoyer. You've made me remember to drink it. I don't really think coffee's really that good. I think it's kind of shit. It's kind of like mud water. You know? I've never had coffee and been like, yeah, that's awesome. But drugs, those are pretty sick. I do this like thing every once in a while. I actually cut coffee recently. I only just started going again recently, but I like just want to prove that I don't need it every once in a while. But then like, so I like cut it for a month or whatever, and then I'm just like, but it makes me happier. The first time you drink coffee after a long break, it just makes you happier, right? And it's like, okay, so what's the downside? the downside is that you drink it more and then you just go back to normal and then you feel unhappy if you don't drink it. But the first few times it's just like only a win. So if you're okay with just trading a little bit of future happiness for current happiness, still recycling the empty cup from no, look, there's stuff in here. You can see it. Look at that. That's a full. There's like at least like this much in there. Not that I should be advertising fucking McDonald's. It's gross. But it's what it is. Okay. So we should have a length field now that makes sense. Okay. Expected type U32 found length of bytes. Oh. So here we need to do like stood mem bytes to value as a U32 and then do the byte order swap, I guess. Okay. Chunk type is mad. Why? No field name chunk type. Oh yeah, because we just called it tip type and data here. And then CRC, I guess we'll just call this a conjugate for now as well. I don't really give a shit. That cup looks huge. It's a little bit big. Yeah, I got the big one because it makes you more happy. The bigger the drugs, the more happy you get after. Okay, so it looks like we have like successfully parsed kind of like the top end of this thing. Now we have a problem where we're hitting an end of file here. So we probably need to track if we are finished. And then I think that if we see, I think it said in the spec, if the file is kind of bookended by the I header and I end. I'm pretty sure we saw that. So I think if we see I end, then we are like fucking dunzo. I assume. I wonder, it's like I end must appear last. It marks the end of a PNG data stream. The chunk's data field is empty. Oh yeah, so I think we just write like, if the chunk type is I end, then we are dunzo. So I guess here, we also then have to extract the type separately. Because we need to check if tip is, I don't know, like equal of I end. Then we set be finished to true. And then here we say if not finished, or if finished, return null to indicate that we are done. That way we shouldn't have an error at the end and we're kind of chilling. Okay, we have a PNG. So now we have to figure out what each of these things are. So maybe we are going to say that we're going to look at like header. I believe the lowercase first letter means that it's not a critical chunk. I think somewhere in here they say critical chunks. All implementations must understand and successfully render the standard critical chunks. A valid PNG image must contain an IHDR chunk, one or more IDAT chunks, and an IN chunk. Now I think that they talk about like ancillary chunks somewhere. All ancillary chunks are optional. In the sense that encoder need not write them and decoders can ignore them. However, encoders are encouraged to write the standard ancillary chunks with the information that is available, and decoders are encouraged to interpret these. But I don't care what they're talking about. Where do they talk about like the chunk type? Right, you can look at like just kind of by guessing here. You can see that like the ancillary chunks all start with lowercase and the critical all start with uppercase. But I'm pretty sure they actually say that here. Chunk naming conventions, maybe. Chunk type codes are assigned so that the decoder can determine some properties of a chunk even when it does not recognize the type code. These rules are intended to allow safe, flexible extension of the PNG format by allowing a decoder to decide what to do if it encounters an unknown chunk. So 4 bits of the type code, namely bit 5 of each byte, are used to convey chunk properties. This choice means that a human can read off assigned properties according to whether each letter of the type code is uppercase or lowercase. So ancillary is the first byte lowercase, private, reserved, safe copy. So we can kind of just say we might be able to like extract some properties about this thing, right? Maybe we'll do something like this, and we'll say that critical is if the first byte is uppercase from type 0. No McDonald's, you might just like the sugar they surely put in it. I mean, I get to pick, but yeah. uh, so we'll ignore non-critical chunks for now. So we'll say if we're critical, we should see this fizz go away. Okay, so these are the important pieces. These are the important pieces. And let's try to extract some information about IHDR, and then later we'll look at IDAT, and then we will look at IEnd, which maybe IEnd is useless. Right, that's very possible. So let's see what's in IHDR. Surely that's in the spec. Okay, IHDR chunk must appear first. Okay. It contains width, height, bit depth, color type, blah, blah, blah. And probably, you just kind of copy this. And slap it here. And we can just go like set a macro that says swap the case of this, go to the next word, write a U, go to the end, back, back. Almost. Almost. Oh, so we need to go, we have to get a little cleverer. Swap the case, find the, oopsies, swap the case, fuck. Here we go. Swap the case, find the colon, go to the next word, type a U, go to the end. There we go. Okay. And then put some, I guess here we look for spaces, and replace with underscores. Okay. And then what? Can we just like fucking like slap this shit? Can we just like if we see this, I wonder if we can just like cast this thing correctly. If we like packed struct here, we might just be able to get away with going like, I don't know, we'll see. We're gonna rename this existing chunk to chunk header. And I think in reality, this critical thing should actually be a function on here. Right? Because we don't actually have to calculate this unless, you know, it's asked for. So this like critical thing, we'll put here. That feels a little better to me. And then now we're gonna be like, known. This is gonna return like a chunk. Okay. And our chunk maybe we'll say like data, like parsed data. Yeah. Yeah, okay. And we'll call this like chunk data or something. That feels kind of right. And I've kind of decided this isn't just the header anymore, because the header is supposed to be, this actually has like the data in it as well. So I'll go back to calling this a chunk. And then whoever is saying that I should write U16 instead of U4 is totally right. You were right. We would have figured that out in a second, but it's nice for you to tell me in advance. And then can we just say like chunk data is going to be a union backed by some enum, and we're gonna be like IHDR is equal to IHDR or something. How do you do this? Like this? Yeah, nice. And now we can say like, I think that we kind of want this to have like a named chunk type. Because then we can kind of do this, where we do like IHDR. Because that way we can do like type. This can be a yeah, we'll do like a parse type. Those 4 bytes in the docs, U16 to U32. Yeah, 4 times 4. 4 bytes, 4 times 8. Yeah, I'm fucking mental. Thank you. Thank you. You're right. You're right. I would have got there. The U4 to U16 tricked me. U1 small feels small for bit depth. That's also a really good point. Sanity checking there. Sanity checks did not pass. So we can do like enum string to enum of self type, right? Otherwise, we return unknown, I guess. So we'll say that we have unknown as a thing that we support in here. Okay. Otherwise, we will try to parse this thing. So can we just say like just like stood mem bytes to value, and we will return this as like switch on the parse type, I guess. If we see IHDR, we return this thing as a IHDR. Yeah, that seems reasonable. Right? So can we do, if it's not critical, continue. Otherwise, we look at it and then we say, switch chunk parse data. If we see IHDR, can we just like print that thing? Header is this. He's mad about something because switches don't have this. It comes here. Did we new line? We did. Critical is now, it's like is critical like this as a function. And then chunk data is missing unknown. So I guess unknown, we can return the data back to say, hey, you, the user of this PNG library, if you know what type it is, you know, externally, you can look at that if you fucking want. Which means that if we see that thing, we just return like the data directly. Like as unknown is equal to this. And here we actually have to return it as a IHDR like this. What is it mad about? Oh, it's equals here like this. Okay, we'll try that. Okay, switch must handle all possibilities. So at 122, we just say else. Panic. I don't know, man. This is fine for now. String to enum does require us to say that we want to parse this thing as a chunk type. Okay, and then do we have to do this? I thought you could just return the void type, but I guess you can't. Oh, it's because we need to return the data now. I forgot that we made that change. Okay, so this looks... I'm not really sure if I think that this is good or not. The width and height seem totally fucking wrong. Oh, but the width and height are in network byte order. Right, I forgot about that. So we have to do stood mem big to native. Okay, I wonder if I could, if this will iterate a struct and do it on every field. That'd be so fucking sick. Byte swap. Maybe it doesn't. Maybe we have to do it on each field individually. Yeah, we do. But I wonder if there's like usage of this thing. Meta, and like if there's like some sort of like meta function that calls this. No, but we can just make one. We can say like byte swap uh fix struct endianness, which will take in some thing, right, and return type of s back, right? And we can just go like for stood meta fields on type of s. We have some field, right? And we might be able to do like ret is some sort of like this thing, right? We go over each field of the input and we say like field s like this, I think. We look at the field of s and we say ret is going to be equal to fix struct endianness of this thing, right? Now, obviously, we have a problem here where if it's not a structure, this is going to fall the fuck over. So we have to probably switch on the type info here. Right? And what's this language? This is Zig. Zig. So if we have a struct, we have some sort of struct info. And what does this give us? We have fields in here already, so we don't need 4 meta fields anymore. We kind of just have fields. And I think this actually has to be an inline for comp time iteration, I think. And then I guess this kind of goes here, right? Then we have our special case of integer. And I think this will tell us signedness in bits. Can we just do like byte swap or stood meta native big stood mem big to native? So he needs the type here, which I guess is just the type of the input, because I don't think that's stashed here. No, he just has signedness and stuff. He's like extra information. And then the value itself, right? So I guess that's S. Right, so we just like kind of swap this shit. Else compile error unsupported cannot swap endianness of, and then we add in a compile time string of like struct. Can we get the name of a structure? Tag name? I don't feel like this is right. Zig name of type. I guess it's probably like type info. Probably, it's probably in here somewhere. Oh, I guess it's on the type. Not sure. Type name. Was that thing? Yeah, it is. Nice. Thank you. Thank you. Okay, so now we should be able to call somewhere. We call fix struct endianness on this thing. Endianness. Okay. That looks right now, right? So we have width 101, height 77, bit depth 8, color depth 6. Nice. Fucking killing it. Fucking killing it. That 101 by 77, I believe, is correct. Yeah, 101 by 77, it says that in the bottom right here. So we are chilling. That looks like an I header ready to fucking go. Let's look at the data field next. Just posting the smile in chat's kind of funny. Yeah. He is a smile. Okay, IDAT. This contains actual image data. Create this data. Begin with the image scan lines represented as described in the image layout. Okay, I don't really care right now. The layout and total size of this raw data determined by the fields of iHeader. Okay. Filter the image data according to the filtering method specified by the iHeader chunk. Jeez, okay. And then compress the filtered data using the compression method specified by the iHeader. So this is on creating. To read the image data, reverse process. Right, of course. There can be multiple IDAT chunks. If so, they must appear consecutively with no other interleaving chunks. The compressed data stream is then the concatenation of the contents of all IDAT chunks. The encoder can divide the compressed data stream into IDAT chunks however it wishes. Multiple IDAT chunks are allowed so that encoders can work in a fixed amount of memory. That makes sense. Presumably that means that decoders could as well. Maybe not. It's important to emphasize that IDAT chunk boundaries have no semantic significance and can occur at any point in the compressed data stream. Right, okay, so we take all of this stuff, we put it into like one buffer, and then try to decompress that thing. Okay. A PNG file in which IDAT chunk contains only 1 data byte is legal, though remarkably wasteful of space. Okay, sure. So I assume that we need to, like, this bit depth, color type, and compression method, like all of this seems kind of important, right? But for now, maybe we start by just trying to get the data. So for now, I don't want to continue. I don't want to keep doing this forever. But for now, we'll just say that the data, compressed data, PNG, yeah, like compressed data, I guess we'll call it. Sure. We'll say that we have some data that we initialize the sim allocator, defer, compressed data, deinit. And for now, we'll just say if we get an IDAT chunk, which we need to support, we will just kind of shove that shit like this. So this is just going to take the data directly, right? There's really nothing special to do here. Pardon my ignorance, but why not just use STBI? Because we don't want to. There's no good reason. But the goal, as usual, the goal is not to actually make something that is useful as much as it is to try to understand things about the software that we use, right? So by writing our own PNG decoder, we will gain intuition about possible problems that we might hit when decoding PNGs, right? Making square wheels so computers around. Oh yeah, I wrote that somewhere. That's like maybe in my description or something. Yeah. So typically we don't really care about doing the best thing. In the real world, you would use STBimage. In fact, in the real world, you might even use libpng, right? You might get a little crazy. But there is something fun about having no dependencies, and there's also something fun about understanding. You know? Big fan of reinventing the wheel for fun learning. Me too. Me too. That's why we do it. Okay. So presumably now we have like some IDAT, and if we get some data, we should just kind of do like compressed data, append slice of D, right? Which is wasteful. So in the future, we can probably find a more intelligent way to do this later. So maybe we should do like streaming decompression. But for now, this will work. And then if we see IEnd, does IEnd have data? Data field's empty. So this we just do nothing, I guess. So here we have IEnd goes return IEnd. Okay. I guess it's maybe like this is kind of nice here. And then here we have IEnd, and IEnd is void. No data associated. So if we see IEnd, we're donezo. Let's just make sure that we're chilling there. Handle all possibilities. We need to handle unknown. And for now, we'll just say panic. Panic! Okay, cool. So we have successfully walked all of this stuff, and let's try to like parse this data. I think it doesn't make sense to talk about IEnd as a chapter anymore because, you know, we don't need it. It has no relevant information in there. And now we just need to like look at this compressed data. So I'm curious to see if our shitty zlib thing will work for us here that we've been working on in happy hour. So let's just kind of like copy paste that shit. And do this. And we should have in here like a deflate decompressor that we can use. So I guess that means like this probably has to be public. And like probably this has to be public. The rest probably doesn't really matter. And there's no like, I think the allocator at this point is just like temporary, so I don't think we have to worry too much about it. And I think that we should be able to call like deflate decompressor using our alloc and some backing buffer. I guess first we need to like confirm, we need to like decompress this stuff kind of like depending on the parameters in it, right? He has like a compression type in the header field, and we must have to like look at that in some way. So maybe it makes sense for us to kind of pull out like this loop here into like load PNG. Maybe not, because I want this to be streaming later, so maybe I don't want to do it that way. Instead, we must have to like look at the header. The header has to come first. We saw in the spec that the header has to come first, right? So we can actually assume, we can kind of do like a first step. Right? And we can say header parse data. So we can say like if header is equal to null, say like return error no header, and then we can say if header is not equal to iHeader, we can say this is, I guess, or else return error no header. Return error not iHeader. And then we can do header parse data iHeader. We can do this, right? So maybe we'll do header. Header chunk, I think is the better word here. Then we have a header, and we can say, we can then do like our checks here on the header, right? So we can say switch, let's see. What's in this thing again? Compression method. So can we look at the compression method here? Compression method is a single byte integer that indicates the method used to compress the image data. At present, only compression method 0 inflate decompression with a 32k sliding window is supported. So here we'll just say if header dot compression method does not equal 0, we'll say return error unknown compression. Otherwise, we can say we can construct our decoder, our deflate decompressor, where we can have an allocator and a backing buffer. So we know that our backing buffer, deflate buff, has to be 32k sliding window, right? Because that's what it says here, 32k sliding window. So we should be able to go 32 times 1024. And we'll just put a comment here that says compression method 0 is deflate plus 32k window. Okay. And what's the last parameter here? The data reader, who converts into a bit reader. So we can actually, this is kind of fun. If we implement like the read API, we could make a reader that extracts IDAT segments, kind of like lazily, as someone calls read. I'm not gonna do that right now, but we could do like streaming decompression here. Instead, what we will do is we will do all of this at the end. Yeah, so we will extract all the data and then just create like a fixed buffer reader, fixed buffer stream over, oh, I think you can just do like compress data.reader. I'm pretty sure that's like a thing that exists. Oh, unless it's only writer. Yeah, he only has writer, which means that the reader is stood IO fixed buffer stream around compressed data items. Okay. Which means that we can pass in FBR reader here. Okay. Deflate decompressor. I've been watching your stuff since the Fuse task project. Ever thought about making edited shorter videos but complete projects? I'm considering it. Typically, we don't finish projects, which makes it a little bit trickier. But I have been working on a blog post for the GPU stuff, which could also be turned into a video. Not really sure if I'm going to do that, but at the very least, a blog post makes a lot of sense because there's like a whole world of people who can be hit by like text and not by video. And if we are, unfortunately or fortunately, I don't know whether it's good or bad, streaming success looks like more viewership by some definition of success, right? So I've been working on it because I think that's like an important thing to capture a bigger audience, but I will post it somewhere. I don't really know how to like get the word out once it goes live because I don't have like a Twitter or anything, but I guess I'll like maybe post it in like a YouTube thing and on Discord or something when it's done. Anyways, not that it matters. Yeah, I'll consider a video as well, but I don't think I'll do one. It just seems like work. I don't want to do. Okay. So how does this thing work? We iterate this thing. And this gives us like a buff pair. And then can we just like, I guess we want like decompressed data as a stood array list of U8s. And I guess as we walk this thing, we're basically going to say decompress data, append slice the first half of this thing and the second half of this thing. And it would be cool if that worked. I'm kind of hesitant to believe that it will, but there's like a chance. He doesn't like this for some reason. That's true because this type is not handled that way. So can we do like a we'll just call it twice, fuck it. Header parsed, I guess we could call it. Fine. Header parsed, and then Header parsed here. All right, let's try that. Okay, so he expected something down here. Probably the decompressor has to be variable, almost certainly. And then he found const again. I didn't hit save. That's why. And then expected optional type. So I think I forgot to write try here because this thing can fail. And reached unreachable code. So this is in the decompressor. We are hitting a case where the length of a uncompressed block is larger than the window size, and we don't handle that right now. But that's fixable. That's fixable. So we just have to return this thing every 32K. So that means that, like, okay, our decompressor, deflate data, comes in as a stream of bits. The bits, there's like a little small 3-bit header at each block. And then each of those blocks can be like compressed, uncompressed, and the compression version can be like with dynamic data or like a static lookup table essentially for what that data means. And we have made like an iterator of this thing, but we need to, we have like an internal buffer that we're using for this thing because as you decode data, you have to be able to like look backwards up to 32K bytes back to like basically say like, oh, if this thing happened over here, I'll put it again over here type shit, right? And so since our buffer is only that large, our iterator has to return every 32K byte, every 32K. And we don't handle that right now. So we just have to say like, we are in a current block and our current block, we need to do something here where like our current block can't just be like the block header. This needs to be like a block state or something. And he's gonna take in the header for sure. So he's gonna have like header is a block header. And then we also need like offset. How far into this have we gone? And I think that kind of fixes this. So here, when we create this block header, we'll do like something that's like header is equal to this, and then this offset is equal to 0. And then here, we need to say like, I guess we need to stare like the length and the offset as well. Then here, if we're in a no compression section, we stash the length as like current block len is equal to this instead of the length, like that. Maybe we still keep this and we just also duplicate it into the current state. So here we need to do like if self current block len is equal to 0, then we populate this. Yeah, that makes sense, I think. Like this. We have to validate the inverse length later. Fix me validate one's complement. But then now we can just say like, we're going to use the offset value as our like starting position here. And we're going to go like, we have to say end is going to be something that's like, I guess this is going to be the like read len or this iter len. Yeah, that makes sense. And we're going to say that it is the like minimum of the backing buffer length or the current block length. That seems reasonable to me. And then we are going to read for 0 this iter len. And then how do we determine that we've like already started? This has to be minus this. We need to look at like the current block length minus how far we've already read. That kind of feels right to me. I think that's right. And then we determine that we're done if the current block offset is equal to the expected len, right? We're kind of done this segment, but we have to increment the offset. So you say current block offset plus equals this iter len. Okay, I think that's right. I'm pretty sure. No fail name B final, because now B final is behind the header. And then also B type is also behind the header now. We hit an end of stream, which is annoying. Okay, which means that I think that I don't really want to sink more time into making our deflate decompressor work right. I think that we are finding now that it's a slightly too complex, and it's not the problem we're trying to solve right now. So it was worth taking a slight peek to see if we could fix like a small issue. But we are not quite there yet. So instead, we'll just link against libc. Fuck it. And we'll decompress with a real library. Because this isn't the problem we're trying to solve right now. So to get decompressed data, we have to call, we'll call zlib is equal to c import c include zlib, or z I think it is, just libz, zlib.h, okay. That looks fine. And then how do we decompress this stuff? We need to like call inflate or decompress. There's like compress functions. Are there uncompress? Uncompress. So we need to check, we need like the right amount of output space, which we can probably guess pretty reasonably, right? We can probably guess this based off the header. So we can probably say that like we need at least the header width times header height times header bit depth over 8, right? We need at least this much space. Right? Surely. And I assume we don't need more than that. That seems like a pretty good guess. And let's just call uncompress now on decompress data pointer, decompress data len, and we have like source data, which is going to be the compressed data items pointer and compressed data items len, right? Now I think that this actually is going to tell us the output in dest len, right? So here we need to say like decompressed len is equal to this, and we pass this into decompressed len, and then we say we look at decompressed data from 0 to decompressed len. Data slice or something, I don't know. Maybe we call this decompressed data buff. And then now we can use decompressed data as this. Boom. Okay. So then can we like, let's just start here. And then also we need to check if zlib ret is not equal to zlib z okay. Return error decompression failed. Boom. We'll start here. How's that looking? He's mad because link library Z is no good. Really? Really? Link library. Oh. It's link system library. My bad. My bad. You can chill. Okay, let's see. Cool. Compiles and does run. Decompression failed. That's not good. Oh, because this isn't a libz thing. This is a deflate thing. Oh, that's annoying. Does this like give us deflate? Can I like just can I use inflate but without the zlib header? Can I use like zlib without zlib header? How to fix a zlib file? No, I just want to like run like libz deflate no header or inflate no header. Like, does somebody have the answer here? Inflate raw? Nope. This is also on some like fucking node thing. Let's see what this guy says. Inflate init 2. Ah, here we go. There's another version of inflate init with an extra parameter of the fields. Next in available zalloc and z3 must be initialized before the caller. Is the base 2 logarithm of the maximum window. It should be in the range 8 to 15. Window bits, blah, blah, blah. Window bits can also be 0 to request. Okay, so does that mean there's decompress or uncompress 2 as well? That'd be kind of sick. There's compress 2. Oh, but that's not really what we want. Yeah, okay. So we'll just kind of have to do it the manual way. That kind of sucks, but whatever. Whatever. The color scheme is Sonic-Eye, but it's fucked up looking because term GUI colors is off for some reason. I don't know, right? This is what it's supposed to look like, but this is what it looks like instead. I don't know. It just kind of ended up that way, and I've never changed it. Okay. So I want to confirm here that like I mean surely okay, what is like deflate init 2? This is another deflate init with more compression options. Does this thing like not output a header? I kind of want to like confirm that that's true before moving on. This is also not helpful. Inflate init 2 no header. Does that let's see. From the manual. Man zlib? No. What about here? This is just the same as like this is just the same as the header, I think. The header type is detected automatically. If requested when initializing with inflate init 2. Inflate will decompress and check either zlib wrapped or gzib wrapped deflate data. The header type is detected automatically if requested when initializing with inflate init 2. Any information containing the gzip header is not retained unless inflate get header is used. Headerless with no zlib header, I think I saw here. Window bits can also be negative for raw deflate. Ah. Okay. So does that mean that inflate init 2 can use window bits? Can also be -8 to -15 for raw inflate. That sounds like what I want. That's cool. Okay. We got there. We got there. So we should be able to call inflate init 2, which takes in a stream, right? Z-stream and window bits. So we have Z-stream is a zlib stream. We initialize this thing with -8. What's like log? We want like a log 32k, right? 32 times 10 to the 4. Log that, divide by log 2, 15. So we want -15 here. -15. Are you on NixOS or just using NixShell? NixOS, but I don't think it really matters that much, to be fair. So then, once we have this, we should be able to call just like start spamming inflate, I think. Inflate. Where is this thing? Here we go. So inflate decompresses as much data as possible and stops when the input buffer becomes empty or the output buffer becomes full. It may introduce some output latency, except when forced to flush. Reading without producing any output. The detailed semantics are as follows. The inflate performs one or both of the following operations. Decompress more data, generate more output stream. So before call inflate, we should ensure that at least one of the actions is possible by providing input and or consuming output. Okay. The flush parameter of inflate can be one of these. Sync flush requests that we get as much as possible with the output buffer. Block requests that we stop when it gets to the next block boundary. Okay. We return ZOK if progress has been made. ZStream end if the end of the compressed data has been reached and uncompressed output has been produced. Or need dict if that's okay. So we should just be able to be like, first we need to check that this is succeeded. So zlib z okay. Return error init zstream. Then we say while true, we try to call inflate on this thing. And we don't really care about flush until, because we're just going to keep going until we get to the end. So here we'll say if this is not equal to zlib z okay, return error inflate, okay. Then, I guess no, we want to say like ret is this, right? And then we switch on ret. If ret is zlib z stream end, we're chilling, we break, we're out of this fucking loop. If it's z okay, we do nothing. And then otherwise, we return error inflate, right? Okay. So before we did this though, we did forget that we have to set z stream out data to our decompressed data buff. And the next available out is going to be the length of this thing. This thing is a uint, so we probably need to like incast this. Okay. then at the end of this, we have our decompressed data as this from the Z stream total out size. I'm pretty sure that's right. And we'll kind of see if this like falls over. He's mad about something. I don't know if this is on crash. Like, I don't know if this is like on module load. He's mad at ZStream alloc. I was under the impression that it uses the default allocator. We're all linking libc. And I thought I saw in the docs earlier that if we don't set the ZStream parameters, it's totally fine, right? If zalloc and zfree are set to znull, inflate and it updates them to use default allocation. Oh, we have to zero initialize this struct. Not undefined initialize it. My bad. Okay, so we are seeing an inflate error, which is not good. So can we like maybe get some information about that? Can we say like else we'll still return error inflate, but can we say what the error was? Maybe that'll give us a clue of some form. Inflate error, -5. Okay, so what's going on there? -5. Buff error, what is that? So inflate. Z buff error, okay. So where are we looking? This is on deflate. I want it on inflate. So that's here. Inflate, yeah. Z buff error if no progress was possible or there was not enough room in the output buffer. I guess we didn't set the input buffer, huh? So pretty important oversight. So compressed data items pointer and available in is going to be len, and this probably has to be incast. Okay, so now we got error 3, which is different. So -3 is Z data error. So this is kind of indicating that what we got is not valid zlib data, right? If the input data was corrupted, input stream not conforming to the zlib format, or incorrect check value. If Z data error is returned, then application may then call inflate sync. So I wonder, can we like see how if we get through some amount of this though? Block inflate smile. Right? Can we just like see if we get like ZOKs along the way? No, we only ever get like a -3, which doesn't seem good. Which does not seem good. There's a chance that we are using this wrong, right? That's definitely possible. So can we read this a little bit more carefully? So on inflate, decompresses more input starting at next in and update next in and available in accordingly. So that seems reasonable. Or we generate more output and next out and available out are updated. Okay, so it seems like the compressed data is in fact supposed to be read here. We can test. We can bisect this problem by zlib compressing some data and just double checking that we're like using the decoder, the like decompressor correctly. So we can do like open test zlib as a binary thing, and then can we do like zlib compress hello world. And then do like f write data. A bytes-like object is required, not a string. So I think I write B here. Okay, so we have some zlib data, and I happen to know that the zlib header is 2 bytes, but I guess for now, what if we did zlib compressed is some data that's like stood fs current working directory. Maybe we'll call this zlib f, I guess. So we'll open a file of test zlib with, you know, some parameters. Then can we do like zlib f read? This needs to be tried to open it. Read to end. With like, I don't know, some fucking max. Can we look at like compressed data 2? I don't fucking know, man. Then can we do inflate init like this? Does this take 1 parameter? Yeah, and then can we use compressed data 2 here instead? Does that work? Read to end alloc does require an allocator, and he probably does need this stuff to go away at the end of the block. Okay, fuck GDB for a second. And he's mad about items here because this is not a dynamic array, I guess. Okay, so that worked. Okay. Right, if we look at decompressed data, like this. We are seeing our little hello world here, which is good. It means that like we're using this API correctly. Now, I wonder if we can get away with like using inflate init 2, right? And then trying to use the compressed data without the header, right? So you can do something that's like, can we just like strip off like the first 2 bytes, which is the length of a zlib header? He's mad about init zstream because this is gonna be -15, my bad. And that also works, right? So the idea here that we can strip the header or something and use raw decompression works great, right? Because again, if we take this inflate init 2 off, he's going to try to read the zlib header. It's not going to work, right? Which is kind of what we expect. So we should be able to like decompress raw deflate data, which kind of indicates that like the compressed data we're getting is wrong, which is kind of surprising. Because here it doesn't seem like we're doing anything crazy. Unless we fucked up reading of the PNG specification. So compression method is a single byte integer that indicates the method used to compress the image data. At present, only compression method is 0. Deflate inflate compression with a 32K window is defined. All standard PNG images must be compressed with the scheme. The compression method field is provided for future expansion. Okay. Decoders must check this byte and report an error if it holds an unrecognized code. See deflate inflate compression chapter 5 for more details. Let's look at chapter 5. Maybe there's like some like extra stuff on here that we don't understand. PNG compression method 0 specifies deflate inflate compression method with a 32K sliding window. Deflate compression is LZ77 derivative used in zip, blah, blah, blah. Further details here, blah, blah, blah. The compressed data within the zlib data stream is stored as a series of blocks. Yep, okay. So it is important to emphasize that the boundaries between IDAT chunks are arbitrary and can fall anywhere within the zlib data stream. There is not necessarily any correlation between IDAT chunk boundaries and deflate block boundaries or any other feature of zlib data. Okay, for example, it is entirely possible that determining zlib check value to be split across IDAT chunks. Got it. In the same vein, there is no required correlation between the structure of image data and a deflate block boundaries of IDAT chunk boundaries. The complete image data is represented by a single DLib data stream that is stored in some number of IDAT chunks. A decoder that assumes any more than this is incorrect. Of course, okay. So then what's the problem? Right? It seems like we should just be able to take all of the IDAT chunks, slap those into one buffer, and use that thing. Right? It seems like that was fine. So why doesn't that work? Print check size of XY, but XY is like irrelevant at this point. Like we have we've confirmed that the zlib header is reasonable, right? Well, I guess we confirmed that it was reasonable here. Let's confirm that it's reasonable here. And then here we should write a panic or returns error duplicate header. Okay. Right, so here we see a header which has a width and height, which is reasonable, bit depth, blah, blah, blah. But like this bit depth and color type and stuff, they're not relevant until we decompress, as far as I understand. So we should be able to be like, compress data, items, pointer, and compress data, items, len here. And I just don't see any reason why this would not be okay. But instead he's saying that we have inflate error -3, which I forgot what it means. -3 means data area. So he's claiming that the stuff in, well, data error and stream error might be subtly different. Z stream error is if the stream structure was inconsistent. For example, next in or next out was Z null, or the state was inadvertently written over by the application. Okay, yeah, so we're in Z data error. We have the input data was corrupted, input stream not conform to the zlib format, or incorrect check value, in which case string message points to a string with a more specific error. Oh, let's look at that then. Let's look at that. So can we look at std log error, data error, and can we look at the thing in Z stream message? All right, let's just kind of see if he says anything sane to us here. Invalid stored block lengths. What does that mean? Stored block lengths. Can we look at like the zlib source code? We might already have it actually. Hell yeah, we do. Invalid stored block lengths. So what the fuck is this? Ooh, there's some tracing? Tracing? How does that work? Okay, hold on. Z verbose comes from verbose. If ndef verbose, define verbose 0. So we have zlib debug. Okay. So I think that we can build this ourselves with debug mode on and just try to like print out some data about the stream that we're running with. I think that's probably the play. So how does this work? It looks like these are just kind of hard coded, unless that's a generated thing. Okay. Looks like we can probably just adjust the makefile here a little bit to do this. Okay. Then, like, surely that we have, like, a library here somewhere. We have libz.a here. So can we, like, force it? Are we a dynamic executable right now or a static one? Like, are we linking libz? Okay, so we should just be able to override LD library path then. To look at zlib like this. And we should we must have edited this in the past, which is kind of funny. So that zlib, yeah, that's not good. That's pretty funny. I wonder what else we changed in this. Okay, so where does this, I forgot we needed to look at where verbose equals, we have like define verbose here, and I guess we just rebuild this with 1. Oopsies. And then can we run here? I want to see like define trace v. We have z verbose here. Can we just like, because there's like probably like a define verbose somewhere else. I don't know, man. Let's just set this to 1 and see if that changes anything. I'm still not seeing anything. Can we look at like LDD of this thing? I mean, he's definitely looking at the right thing. He is fprintfing to standard error. Oh, there's only z error. Where's trace v again? It is just fprintfx. So we are supposed to be tracing to standard error. Did we skip the IDAT chunk header and CRC from the data past deflate? I remember that messing up the deflate stream when I was working on this stuff. Did we skip the IDAT chunk header and CRC from the data? I don't understand how we would have skipped anything though, because I think that like we are just reading every single IDAT and slapping them together, right? We just go parse data. If we see an IDAT, append that slice, and our data here is just like, give me the data if it's IDAT. And then, oh, did we skip? Oh, I think we did skip. I'm pretty sure I see what you're saying. If I didn't skip it, that would be a problem. But I'm pretty sure we are. Unless we're like parsing this thing wrong. Right? It's very possible, but I don't think so. I mean, it's parsing the file okay. Have to be greater than 1, the debug thing? Yeah, that's a good point. That's a pretty good point. That is a very good point. Although we're still not seeing anything interesting there. But maybe like maybe that's like normal. What was the like error we're trying to see? Invalid stored block lengths. It could just be that we're just not seeing anything interesting. Although I would think that we should hit at least one of these, right? Can we do like trace v stood error loop, right? Like let's just see if we're doing something wrong here. Yeah, we're not seeing this at all still, which makes me think the trace v is. I mean, we have zlib debug. I'm pretty fucking sure. Pretty sure. Because our make file, do we have to like make clean here? Right, so like in inflate, we're compiling with dzlib debug. So I don't really see why. I really don't see why this wouldn't be working. Right, we have like. Wait. Did I not put a trace v here? I thought we did this. Let's just see. Now it's just not doing shit? Because of this one trace? Am I fucking high? That's crazy. What the fuck? Am I fucking stupid? Trace v and trace. Okay, so if z verbose. Okay, we run fprintf, right? Right? Which is just fprintf like this. God damn it, dude. Okay. And you're telling me if I write trace v here instead, which just calls fprintf, the behavior is different? Where's it going? Like, am I fucking high out of my fucking mind? I feel like I am. Okay. So it seems like we just don't have zlib debug defined here for some reason, even though the compiler flags have it on. Is it possible that S flags don't contain the C flags? And I need to do this as well? Oh, but we're not in static. I don't think we should be static linking. Okay, so we create a bunch of O files with zlib debug defined. Then we have we build them again. Oh, S is probably for shared object. So for the shared object, we must just not be doing this. I see. So here we want zlib debug here as well. That should get us where we want to go. There we go. Okay. Okay, one more time. There we go. We finally got there. So we get reset, and then we immediately see stored block, and then we have invalid block lengths. Okay. So, okay. So he's reading some bits out of this thing. He's looking at the first 2 bits and he's going, this is a fixed block, and then immediately falling over. So can we actually just like look at our data? Can we look at here and see if we were to decode this thing by hand, if we would come to the same conclusion, which is why it is good that we wrote a zlib decompressor earlier, because now we have like an idea of what we should be seeing. So can we just like print out the like compressed data as a Boolean number, and I want this thing to be padded so that they are always 8 bits. That will help. Okay. I want it to pad with zeros. Do I write 0, 0 here? No. Something like this. Other way though. There we go. Okay. So this is true. According to this data, we have block type 0, B final 0, block type 0. Which is what he's saying. He's saying block type 0 is like static data. Then we know that the next chunk, I think that if you have block type 0, I believe the deflate specification says that you discard everything up until the end of that byte. Any bits of the input up to the next byte boundary are ignored, right? So we read these 3 bits, and we go whoop. Okay. Then he sees the length of the block, which is 2 bytes. And then he's supposed to see a 1's complement of that thing, which I don't really know what 1's complement is. 1's complement. What is that? 1's complement of a binary number is the value obtained by inverting all the bits in the binary number. Negative numbers are represented by the inverse of the binary representations of their corresponding positive numbers. Such a system number is negated. Okay. By computing its 1's comp. Okay, sure. What's the fucking God damn it here. Blah blah blah. An n-bit 1's complement number system can only represent numbers blah blah blah. Am I fucking mental? Is there no like, just tell me how to like convert it. Just flip them. 2's complement is 1's, but you add another bit. Okay, that's, so if we flip this, we do not, if we flip these 2 bytes, we do not get these 2 bytes. Right? Which means something is wrong. It means we must be like missing data. We have to be, right? Unless we're wrong about how we are supposed to grab this data out of the PNG. Everything we read here makes it sound like we just literally rip out the IDATs. But then why does it not work? Right? Let's just do a quick sanity check. Right? Yeah, that's fine, right? So we do not understand something here. So can we look at the data parser again? Let's just double check here. So we believe that the file structure has, each chunk consists of 4 parts: length, chunk type, chunk data. Now, we can assume that our chunk, we have at least parsed the overall structure of this correctly, because we see the I header, IDAT, IEnd. All of those come out okay, which means that we must have pulled out the IDAT section correctly. There's no reason that wouldn't. Otherwise, we have the wrong data. I guess we could be getting the wrong data here, but we call try advanced length, and then this just like takes out the data at that component at that segment. So I don't see why there'd be a problem. And when we try to pull out the IDAT, we just return that data back. So I don't really see a problem there. We're not doing any like endianness fiddling, and I don't think we should be. Okay. Can we assert here just for sanity that the chunk length is equal to the data length, right? Let's just for sanity say that. And it looks like that is fine. We're not crashing, right? If we added like a +1 here, we would crash before that. Yeah, so this is fine. We seem to have like a valid data block, and we seem to only have one of them. And if we hex dump this thing, we do only see IDAT in here one time, right? Maybe for sanity as well, can we maybe print out the data as hex as well? So compressed data items I. 789C ED, which is 789C ED DAC1, right? So DAC1 seems pretty reasonable. Are we accidentally freeing stuff that we shouldn't be? This is only freed at the end of the block, so I don't really believe that seems reasonable either. Interesting. Interesting. Let's read this again. IDAT chunk contains the actual image data. Create this data, blah, blah, blah. To read the image data, reverse the project. Release the process. So this is literally just the first step, decompress the data. Endianness? I don't really see how endianness would be relevant here. I don't see how that would matter, because endianness kind of like applies to how you want to use multiple bytes to represent a large integer. We're not looking at like integers of any form right now. We're literally just trying to decompress the thing that we got. Unless I misunderstood, and maybe the deflate data, is it possible that this is actually not raw? Is it possible that there is a header on this compressed data? And I misunderstood. That seems like a possibility. What if we just call inflate on this thing instead of inflate init 2 with a raw stream? Right? Maybe. Okay. We are getting a lot farther. zlib header, okay. So I just completely misunderstood. They said it's deflate data, so I just assumed. I didn't fucking read. I didn't read. Deflate compressed data streams within ping are stored in the zlib format, which has the following structure. So I'm just like a fucking dumb piece of shit. Aha. Okay, so then we get to inflate error -5 after inflate error 0. So what is that? -5 is buffer error, which kind of makes me think that this is not big enough. Let's just kind of like make this thing larger. And it looks like we got our data. Looks like we finally got our data. So now can we extract the more interesting information here, which is the data itself. Let's see if we can like write this stuff out in a way that makes sense to us. So we'll say interpret image data. God damn it. If only we had read the spec instead of just guessing. Sometimes our approach of just like randomly doing stuff works really well in our favor, and sometimes it really bites us in the ass. But it's okay. You know, I'm okay with it. I like that we came to the conclusion ourselves. Okay. So where is like the header stuff? iHeader. Or I guess it was the IDAT section was the kind of the interesting piece here. So now we have to apply filtering. This implies appending a filter type byte to each scan line. So, okay, filter method. Filter method. Single byte integer that indicates the pre-processing method applied to the image data before compression. At present, only filter method 0, adaptive filtering with 5 basic filter types is defined. So I guess we should say somewhere, if the filter method is not equal to 0, we have an unknown filter method. Okay. As with compression method field, decoders must check this byte and report an error. See filter algorithms chapter 6 for more details. Okay. Okay. So this chapter describes the filter algorithms that can be applied before compression. The purpose of these filters is to prepare the image data for optimum compression. So 5 basic filter types, and we can go by scan line in the image data sent to the decompression step. Each scan line is preceded by a filter type byte that specifies the filter algorithm used for that scan line. Filtering algorithms are applied to bytes, not to pixels. Okay, regardless of the bit depth or color type of the image. So how do we know the scan line size? Presumably to undo this filter, we need to like look at this, hope it's fucking 0, and then hop to the next scan line, right? To reverse the effect of a filter, the decoder must use the decoded values of the prior pixel on the same line. The pixel immediately above the current pixel on the prior line, and the pixel just to the left of the pixel above, blah, blah, blah. Okay. Scanline is transmitted unmodified. It's only necessary to insert a filter. So do we have like scanline size in the header or something? Like width, height, bit depth. Maybe we assume a scanline size based off of the bit depth, width, and width. Right? We could probably make a guess there. And then what is like interlacing? Interlacing. Do we see anything about interlacing in here? Maybe we look at the header here. Header. Where'd it go? iHeader, here we go. So interlace method. Single byte integer that indicates the transmission order of the image data. 2 values are currently defined. 0, no interlace, and 1, Atom 7 interlaced. Section 2.6 for more data. 2.6. A PNG image may be stored in interlace order to allow progressive display. The purpose of this feature is to allow images to fade in when they are being displayed on the fly. I see. Right. So you can like, you get more of the data at once, but we probably don't have that. So we can probably just assert, we'll probably just check that we only get the interlace version that we support, which is no. We'll just say no fucking interlacing, please. And then if we get it, we'll fall the fuck over. So what are the 2 options? 0, no interlacing. So we'll say if header.interlace method is not equal to 0, we'll say return error unsupported interlace mode. Okay. And then that means that we can go line by line, and we're going to assume here scanline size is going to be the width times the height times the bit depth over 8 plus 1, right? That's kind of my assumption here. And then we can maybe assert for now, or let's look at the decompressed size. as well as the scanline size and the height, right? This will tell us if we're right. So we can look at the decompressed data, scanline size, and header height. Oops, this should be decompressed data len. There we go. Because it said that there's one header for each line. Which seems wrong. 7778 times 77 over 4. Well, oopsies. 7778 times 7. Jesus. What the fuck is going on? 7778 times 77. Divided by 4? Yeah, it doesn't seem right. Does not seem right. Oh, oops, not height. I'm a dumbass. Width times bit depth. My bad. Scanline size is 102 times 77. Oops, 102 times 77. Okay. Times 4. 102 times 77. 31185 over 102. Okay, that's wrong. 31185 divided by 77. 405. Okay. So 405 is surprising. This is like the width of one line, right? Or, yeah. We're expecting a width of 101. Oh, yeah. Wait. I think that this is right, because this 405 is 101, which is the width of the image, times 4 plus 1, right? So it's just the bit depth is not really behaving the way I expect. I think. Because that is like a reasonable size to me. Okay, so we have bit depth of 8. Color type. The color type is important here. Surely the color type. So the bit depth is how many bits per color channel, I bet. And I would bet that the color type is the thing that tells us how many bits per pixel there are. Yes. Okay, cool. Cool. So color types we have grayscale, RGB, palette, grayscale, and RGBA. So this is YA. Yeah, okay. Hold on. So this is enum of grayscale, RGB, palette, call this Y for what? So Y for luminance. I don't know. It's just like a way. Don't ask me. Okay. So this should give us a color type like this, and we say we switch on self color type, and we return 02346. Okay. Okay. So this is RGB, palette, YA, RGBA. Y for grayscale is a crazy choice. But I mean, I've seen this a lot of times. That's what the Y in YUV stands for. It's like the luminance. So it is what it is. Okay. So then can we do like a... We might want to do something that's like... I guess we'll just do manually for now. So we'll get the header color type. Color type is going to be header.colorType. Let's just see what we have right now. He's mad because there's an else. Panic, I guess, for now. We'll fix this later. He's mad because value with comp time only depends on runtime control flow. What the fuck is he talking about? I forgot to hit return. Ixme // f space fix me. Shut up, lug. I can fuck it up however I want. Okay, so we have an RGBA thing. So that seems good, right? Now we can just assert stood debug assert that the header color type is equal to RGBA. And then right under this, we'll say bits per pixel is equal to 4. We'll say bytes per pixel here is equal to 4 times the header bit depth over 8, right? And then this is decompressed data buff is like this times bytes per pixel plus 1 times header height. That's what we expect to see for the scanline size. Then when we look at this thing, the scanline size is now header width times bytes per pixel plus 1. And let's see if that's a little bit more reasonable. So we get 405 times 77. Oopsies. 405 times 77 is 31185, which is the decompressed size, which is huge for us. Absolutely mega big for us. So we can go now for 0 to header height or something. And what we're going to do, we're going to just try to like take that data and like slam it out somewhere, right? So we're going to like maybe make some sort of like output file, which you can do like stood fs current working directory create file at output ppm. Okay. And ppm is this like uber simple image format, like where you can just fucking like type a couple of letters in like human readable format, and then just like write the fucking data, right? So I'm just going to we looked at this the other day. I think it's P6 is the one I want. P6 just lets me like slap some binary data somewhere. Yeah, here. So portable pixmap, I have binary data raw, and then I just type P6 at the top, width and height, then slam a jam of the data in there. So we should be able to go like, this needs to write try. Writer. And then we should just be able to be like, writer print. We want to print P6. Maybe we'll do it this way. P6. Width, height. And then that's it, I think. With header width and header height. He's assuming that we have 3 bytes per pixel. So we should just be able to go like data. Okay, so we have like the filter method here, which is going to be data at y times scanline size. Then we're going to hope to God that this filter method is 0. Right? We'll return error unsupported filter method. Okay. And if he's not, then we should just be able to go from like the element after this Then we want to go end is start plus scanline size minus 1. And we should be able to just go like for, something in like the data. How do I look at this? It's like the decompressed data, which I guess is kind of here as well. From start, end. We need to like get this data out somehow. So we'll say like const data pixels is going to be U32 array, I guess. Sure. And we can go for each pixel. We just write out the RGB. So we say writer, write byte of truncate pixel. Truncate pixel should write by 8, and truncate pixel should write by 24, 16. And we should, at the end of this, have like a file that kind of looks the same as the PNG that came in. We need a stud mem slice bytes as slice of U32, and I think that we can just align cast this and hope for the best. Okay. Unsupported filter method. Fuck! That means we actually have to do work! Fuck! See filter algorithms, chapter 6. Alright. So can we at least print out what it is? Filter. What do we got? What we got? We immediately hit filter 1, which is sub. So what does that mean? The bytes to the left of the first pixel in a scan line must be treated as being 0. Okay. So sub. The subfilter transmits the difference between each byte and the value of the corresponding byte of the prior pixel. To compute the subfilter, apply the following formula to each byte of the scan line. Sub x is equal to raw x minus BPP, where x ranges from 0 to the number of bytes representing the scanline minus 1. Oh, jeez. Okay. Raw x refers to the raw data byte at that byte position in the scan line. And BPP is defined as the number of bytes per complete pixel, rounding up to 1. For example, the color type 2 with a bit depth of 16, BPP is equal to 6. 3 of 2, BPP is equal to 1. Oh, for color type 0 with a bit depth of 2, BPP is equal to 1. Okay, sure. So x ranges from 0 to the number of bytes representing the scanline minus 1. Okay. So what is x then? The subfilter transmits the difference between each byte and the value of the corresponding byte of the prior pixel. Oh, so we go back by 1. So we look at us minus the adjacent pixel. So I guess the assumption here is that we might, if we have like a line that is all green, you can represent that as a fuck ton of zeros, which means that compression will be better because all lines will have a bunch of zeros, despite the fact that they might be different colors. I think that makes sense. So let's just double check this again. So first of all, what if we just didn't fail on the filter method? Right? What we should see is we should see one yellow pixel and then a bunch of pixels that aren't fucking yellow, right? that's kind of like the reasonable assumption here. We did fine. Align cast is no good. So you're saying that I can just write align 1 here. And then this align cast won't work, will go away. Okay, so can we like look at what we got out here? Oh, so that's the fucking PNG. I want the output ppm. Loading image failed. Fuck. Why? Why? Did we crash somewhere? No. So we should have iterated over each of these bytes in the line. Can we look at the... Oh, we forgot to write the... I forgot you have to write 255 here as well for number of bits per pixel. So now can I open that thing? Yeah, okay, look at that. Look at that. Okay. That's pretty fucking sick. Pretty fucking sick. So yeah, we can see pretty clearly, like, if you were to take this, like, yellow piece here and just keep going across, you go say, this is like a sub, and we look at the thing to the left, it goes, same thing. There's literally no difference all the way across, right? And then he literally keeps going onto the next line. And then I guess eventually, we hit black, right? So presumably, I would bet that one of these things becomes like... You could tell that this is marking the end of the eyeball, which kind of indicates that here we probably are marking the start of the eyeball somehow, and maybe it's just like not really a visible thing that we can look at, right? Because it could be that there's like negative numbers somehow represented here. Although I guess every single byte here is visible in the range 0 to 255, but it might be like 1 or something as well, which might be a little bit hard to see. So there's probably something here, but I don't really know what it is yet. There's probably also an up filter in use. Yeah, probably. Not sure. But I think that this is kind of like a success enough for now, right? We can see that we've definitely parsed something. We've got like the overall structure of the PNG down, and now it's just about kind of tying off the last little pieces here. I expect that we're going to have to upgrade a little bit more and try to do so, like, as we get farther, like, parse more images, I'm sure we'll start falling over in other ways. So I think there's probably enough to do to warrant another stream on this. So I think I'm willing to call it here for the day, because it is 4:15, which is around when I like to call it. Yeah, I think it's pretty cool. So thank you for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. If you are watching on YouTube, you might say, how are you streaming from 12:30 to 4 if it's a 2-hour VOD? And the answer there is we split the stream into 2 segments. One is kind of like cleanup / reading / whatever you want to call it, kind of like supplemental content, I call it. So if you were to leave the code in the state that we left it in today, we would hate ourselves in the future. So, or I guess our future selves would hate us today. So what we do is like we kind of say, well, I'm going to be doing some code cleanup. I'll do it on stream, but I'm not going to make a YouTube video out of it necessarily, unless you really, really want to see that YouTube video, in which case, if you join as a YouTube member or you check out the Patreon, those segments of the stream get archived there, but you shouldn't have any problem following along if you don't look at those. Otherwise, what else do we have to say? If you're watching on YouTube, there's a Twitch link in the YouTube description. You can swing by and say hello if you want. If you're online between 12:30 and 4 Pacific time, if you're watching on Twitch, there's a YouTube link in the Twitch description where the archives end up. And we should eventually have something on GitHub here. I don't have a repo yet, but we'll make one. And the code will end up here. Same username as both Twitch and YouTube. I think that's all the plugging. And yeah, let's call it there. YouTube, goodbye. And Twitch, let's find someone to raid.